Good morning, student. Today we will discuss last colligative properties, osmotic pressure and osmosis, reverse osmosis. The topic is osmosis. Before going to discuss the osmosis, we will discuss one new term which is required to understand the osmosis phenomena, that is known as SPM. SPM means semi-permeable membrane. Semi-permeable membrane. It is one type of membrane having a network-like structure, and it is made up of submicroscopic particles. It contains holes, otherwise pores, in the structure of membrane, and depending upon their size, one of the most characteristic of semi-permeable membrane is that it can allow only pass to small molecules. It does not allow to pass the bigger molecules. It can only allow to pass small molecules. Small molecules, that means SPM, it can allow to pass only small molecules. Small molecules, that means it can allow to pass only solvent molecules. Only solvent molecules. That means, remember, in SPM only solvent molecules can pass through it. It does not allow to pass solute molecules because solute molecules having bigger size. Remember characteristic, only solvent molecules will pass through semi-permeable membrane. Now, semi-permeable membrane having two types. Okay, only solvent molecules pass, solute molecules does not pass. SPM having two types. Certain naturally substance act as a SPM, that means natural semi-permeable membrane, natural, and certain synthetic substance act as a SPM. Natural semi-permeable membrane examples like pig's bladder, and we can say parchment, synthetic semi-permeable membrane examples are cellophane. So remember again, SPM can allow only to pass the solvent molecules, it does not pass to solute molecules. Now, osmosis. What do you mean by osmosis phenomena? When solvent and solution are separated by SPM, that means like this. we have two situations when solvent and solution are separated by SPM, and suppose two different solutions are separated by SPM, then what happen? Now remember characteristic, we know only solvent molecules will pass. That means in first situation, net flow of the solvent will start from solvent side to solution side. That means net flow of the solvent molecules will automatically start. Now when two solutions are separated by SPM, then remember always solvent molecules will pass. That means spontaneous net flow of solvent molecules will start from always solution having lower concentration. That means this will be the net flow of solvent, net flow of solvent. Because solid molecules does not pass through SPM. Now we know this will be the spontaneous flow of solvent molecules is start, and until the equilibrium will be established. This phenomena is known as osmosis. So again, what do you mean by osmosis? So when solvent and solution, otherwise two different solutions having different concentration, are separated by SPM, then net flow of the solvent molecules will start. In first case from solvent to solution side, and in second case solution having lower concentration to solution having higher concentration. This phenomena is known as osmosis phenomena. Now, based on osmosis, we have new term osmotic pressure. Osmotic pressure. What do you mean by osmotic pressure? We know in first case solvent molecules start to move from solvent to solution side. Here atmospheric pressure is 10 PATM. Here also atmospheric pressure is 10. Now if we want to stop the spontaneous flow of solvent molecules will move from this side, solvent to solution, again from solution having lower concentration to higher concentration. Then we have to apply the pressure opposite side. That means here we have to apply the pressure. In case of first case solution side, and in second case here we have to apply extra pressure. That means some extra pressure is required. We can say pi. That means the minimum pressure which is required to stop the osmosis phenomena, then this pressure is known as osmotic pressure. That means definition of osmotic pressure: the minimum pressure which is required to stop the osmosis phenomena. Is called That means the minimum pressure which is required to stop the osmosis phenomena is called osmotic pressure. In first case, we have to apply osmotic pressure on solution side, and suppose we have two solutions having different concentration, then we have to apply the pressure on solution side which having higher concentration. Here we have to apply. Now, how to calculate osmotic pressure? The experimental result shows that for a dilute solution, osmotic pressure having symbol pi. So for dilute solution, this osmotic pressure is proportional to its molar concentration. That means pi proportional to C. C equal to molar concentration. Remember, at a particular temperature, that means at given temperature. Suppose temperature is T, then we can write pi equal to Cp. For dilute solution at the given temperature, C molar concentration, temperature T at temperature T. That means osmotic pressure depends upon temperature also. When the temperature changes, osmotic pressure will be changed. Now here proportionality constant is R. That means we can write pi equal to CRP. Remember, to calculate the osmotic pressure. That means osmotic pressure depends upon molar concentration and temperature. Temperature changes, osmotic pressure changes, molar concentration changes, osmotic pressure changes. So remember this formula useful for the calculation purpose. Now we know how to calculate the molarity, molar concentration. Molarity means mole per liter. So C equal to N2 by V. 1 means solvent and 2 means solid. That means moles of solid divided by volume of solution in liter. That means pi equal to N2 RT by V. Again, how to calculate moles, given mass upon molar mass. Therefore, pi equal to W RT by M2 into V. W2 means mass of solute, M2 means molar mass of solute, V volume of the solution in liter. So by this way, you can calculate the molar mass of solute. That means M2 equal to, remember, W2 RT upon IV. So this is also one of the method to calculate the molar mass of solute. We have 4 methods. First one is based on lowering in vapor pressure, second elevation in boiling point, depression in freezing point, and finally based on osmotic pressure. Mass of solute we know, R means gas constant in a proper unit. Suppose we want to calculate the pressure in atm, then 0.08205 liter atm per mole Kelvin. Suppose we want to calculate in bar unit, that means 0.08314. Temperature is always in Kelvin. And here remember, V is volume of solution. Volume of solution is always in liter. This will be V always in liter. Remember, temperature in Kelvin, Kelvin unit. Pi, suppose we want to calculate in bar unit, then value of R equal to 0.08314 meter bar per mole Kelvin. W2, mass of solute in gram. So we can calculate the molar mass of solute by using this formula. That means there are four methods to calculate the molar mass of solute based on colligative properties. Now again remember this osmotic pressure is colligative property. Colligative property means it depends upon the numbers of solute particles present in a solution. It does not depend upon the nature, only depends upon the numbers of particles of solute present in solution. Now to calculate the molar mass of solute based on different colligative properties, this osmotic method having advantage to calculate the molar mass of solute like proteins, polymers and macromolecules. So, why osmotic pressure method is used to calculate the molar mass of protein, polymers, macromolecules? So, from given four methods, that means based on colligative properties, osmotic pressure method is used. What are the reasons? The first reason is in other methods molarity is used, while here osmotic pressure we are using molarity. It is based on molarity. Second advantage is this method is work on room temperature. Suppose in elevation in boiling point heating is required, depression in freezing point, then we have to lower down the temperature. Here heating and freezing is not required. That means this method works at room temperature. Again, in other methods, the change in value in colligative property, that means elevation in boiling point, depression in freezing point, otherwise lowering vapor pressure, this change in value is very low. That means we are facing difficulty experimentally to measure such type of smaller values, while in case of osmotic pressure, value of osmotic pressure is comparatively high to other colligative properties, so we can measure easily. That means third advantage is osmotic pressure value is high. That means pi is high compared to other colligative properties. Now fourth one, suppose we want to measure the molecular mass, otherwise molar mass of biomolecules, then using elevation in boiling point method, heating is required. Biomolecules are unstable at higher temperature. Again, suppose we are using to calculate the molar mass of polymers, and then it having low solubility. So it is difficult to measure the change in value of other colligative properties. That means for biomolecules which are unstable at high temperature, that means heating is carried out, then elevation is boiling point method is not useful. Again, proteins, otherwise polymers. Polymers having low solubility. The change in colligative property will be very less. That means finally conclusion is to determine the molar mass of protein, polymers and the macromolecules. Always osmotic pressure method is used because it having following advantage over other methods. Based on osmotic pressure, solution can be classified into three categories. The first one is isotonic solution. Isotonic solution. Second one is hypertonic solution. And hypotonic solution. Isotonic solution means the two solutions having the same osmotic pressure at the given temperature is known as isotonic solution. That means it having the same osmotic pressure, then it is known as isotonic solution. That means when isotonic solutions are separated by SPM, then there is no osmosis phenomena because both solutions having the same osmotic pressure. Now hypertonic solution, hyper means more. That means when we are comparing two solutions, otherwise 3 or 4 solutions, then the solution which having more osmotic pressure is known as a hypertonic solution. That means more osmotic pressure. That means suppose two solutions, then the solution having more osmotic pressure we have to consider. Suppose more than one solution, then solution having the highest osmotic pressure is known as hypertonic compared to remaining solution. And similarly hypotonic solution, that means having a less osmotic pressure. That means we have two solutions. Then the solution which having the less osmotic pressure is known as hypertonic solution. Say example, suppose we have solution A, solution B and C. Solution A having osmotic pressure 5 here we can say 0.1 bar. Osmotic pressure is in bar. Here we can say 0.2 and 0.3, and the solution having 0.4 bar osmotic pressure. Okay, isotonic, that means again we write here 0.1. Okay. Now as per definition, isotonic solution same osmotic pressure. That means A and solution B are isotonic. A and B are isotonic because 0.1 same osmotic pressure. Now in this solution which having highest osmotic pressure, so C solution having highest, so C is known as hypertonic solution compared to A, C and D solution. Again which having the lowest osmotic pressure. The lowest osmotic pressure, that means solution A, otherwise solution D having the lowest osmotic pressure, that means it is known as hypotonic solution. Now in a red blood cell in our body, that means RBC, the fluid inside the red blood cell having osmotic pressure which is equivalent to the normal brine water solution, that means RBC in which the fluid having osmotic pressure which is equivalent to osmotic pressure of 0.9 percentage W by V NaCl solution. That means when we are calculating the osmotic pressure of this solution and the fluid inside the RBC both having same osmotic pressure, that means these are isotonic solution are there, because under same temperature they having same osmotic pressure. Now what happen when RBC is kept in a different solution? So we have three cases. First one and second and third. Case 1, case 2 and case 3. Now in first case we have solution of 0.9% W by V NaCl solution is there. In second case we are keeping solution having the lower concentration. That means here suppose 0.4 percentage W by V NaCl solution is kept, and here more than 0.9, that means we can say suppose 1.1 percentage W by V NaCl solution. Now this solution and the fluid inside the RBC having the same osmotic pressure. That means when we are putting RBC, okay, now RBC fluid inside having the same osmotic pressure like this, that means that this solution is isotonic. That means we have kept the RBC in isotonic solution. Now again this will be second case, concentration is lower. That means obviously osmotic pressure will be less. That means we have kept RBC in a hypotonic solution. Now again third case. Higher concentration, that means osmotic pressure will be more. That means this solution is hypertonic compared to the fluid inside the RBC. Hypertonic. Now what happened? Here fluid inside the RBC and outside 0.9% W by V NaCl solution, same osmotic pressure. That means no osmosis phenomena occurs. This outside wall of the RBC act as a SPM. That means semi-permeable membrane. Now osmotic pressure is same. That means here no change. That means no impact on RBC. Now here in a hypotonic solution concentration is low. That means here low concentration inside RBC fluid having higher concentration. We know as per definition osmosis always made of solvent molecule start from solution having low concentration to high concentration. That means flow will be like this. That means size of the RBC is increasing. New size, that means swelling occurs. You can say that means RBC cell will be increasing in size, swelling occurs, and finally more solvent molecules will be passed. Then it will be collapsed. Now, when it is kept in a hypertonic solution, so here concentration is outside high, here concentration is low. That means solvent molecules from RBC, that means go outside, that means like this. That means size of the RBC is decreases. This will be new size. That means in short shrinking occurs. That means size of the RBC is decreases. That means finally conclusion, when it is kept in isotonic solution, no change. When it is kept in hypotonic solution, then swelling occurs, size increases, and when it is kept in hypertonic solution, then size is decreases, shrinking occurs. Now next point is RO. That means we know osmosis now, reverse osmosis. Reverse osmosis. What do we mean by reverse osmosis? So obviously name suggests we have to make the reverse osmosis phenomena. That means when we have to apply the pressure, that means this is pi. Pi is the minimum pressure which is required to stop the osmosis phenomena. In first case we have to apply in solution side, in second case solution having higher concentration. Now suppose we are applying the external pressure greater than pi, then what happens? Pi is the minimum pressure which is required to stop the osmosis phenomena. We are applying greater pressure, that means when external pressure P external is greater than pi. When we are applying external pressure greater than osmotic pressure, in first case solution side, in second case solution having higher concentration, then the flow of the solvent becomes reverse. Flow of the solvent becomes reverse, and this is known as the reverse osmosis. Again remember, osmosis phenomena is a spontaneous phenomena, that means occurs on its own. In case of reverse osmosis, it does not occur on its own. We have to apply the pressure, and which must be always greater than of osmotic pressure. Then reverse osmosis takes place. Now, main use of reverse osmosis is desalination of water. Desalination of water. That means you can purify seawater with the help of concept of reverse osmosis. That means suppose in a solvent we have kept pure water. Here seawater is there. Then when osmosis phenomena take place, the flow will be like this. But when reverse osmosis, that means from solution, flow of solvent will be take place. That means pure water. That means flow of water takes place from this side. That means we can obtain pure water by applying the principle of reverse osmosis, and very high pressure is required in this situation. Various membranes are available for the desalination purpose. One of the famous is cellulose acetate. Cellulose acetate. Cellulose acetate membrane is widely used in desalination of water, and this water can be used for the drinking purpose. In various countries, they are using desalination plant to satisfy their drinking water purpose, and when the demand is more for the drinking water, then we have to apply the principle of reverse osmosis. So this is the discussion of osmosis and reverse osmosis.